I'll start recording. So did people read stuff? Yes, no, a little bit, no. That's good. From the first set of things. There were 3 readings from 2 books. One was like a bit in Arnold. Then there was the first 4 pages of Landau, and then it was another bit in Arnold. But the other bit in Arnold was like less interesting. Well, it was interesting, but less important. This was in announcements channel, but that's okay. It doesn't matter. So let's recall something. So right now, what have we done last time? That's true. What have we done last time? Yeah, that's good. So we kind of talked about Newtonian mechanics, and then we said like, okay, if you here's how we set up classical mechanics using the Newtonian way. You have F equals ma, so on and so forth. One thing we noticed that it would be nice if you could write down some potential function, right? That was one thing. And we talked a little bit also about phase diagrams, that you can rewrite F equals ma as as instead of one single equation, you can write it as 2 different equations in terms of x dot and x, right, as different variables. And then you had this phase plot, and then you could kind of study the behavior of solutions without and how a system would move around, at least in phase space, without necessarily having to solve the equations. Okay, you could kind of guess what the behavior would be like. Okay, right now, what we're going to talk about today, we're going to try and rewrite. So we're going to look at a different way to formulate classical mechanics. So it's a completely different way. And I think what I'll do is first we'll do a little bit of math. Then I will kind of state the assumptions of this new classical mechanics. And then we'll maybe try and see how it connects to what we did with F equals ma before. And maybe we'll solve 1 or 2 simple examples. Okay? Yeah. I don't know exactly everything else, but okay. So one thing we need to do is we need to revisit what we were talking about with derivatives. So what do we want? One of the first times we defined this idea of a directional derivative, right? So definition. What was the setup with directional derivatives? What did we have?
There was a vector of direction we're going in, and then we turned it into a single dimensional derivative by like adding a scalar multiple of that vector.
Exactly. So first of all, you have a vector space. So let V be a vector space over R. So let V be a vector space over R. Okay, good. And so let f be some function from V to R, not necessarily linear, it could be any function. So then the derivative at V naught in direction u is given via worth. So I'll write it like this. You can think of by epsilon f of v naught plus epsilon u, which is really the limit as epsilon goes to 0 of f of v naught plus epsilon u minus f of v naught divided by epsilon. Okay? So, the idea is we're at point, you have some kind of vector space, right? You're at some point v naught, and you say, suppose we go a little bit in some direction u, right? And you just kind of say, okay, let's go a little bit in direction u. Look at what the value of the function is there, subtract it from here, and then divide by epsilon. So you essentially take a usual derivative, just in a particular direction. Yeah. Okay, this makes sense. And then we remembered that the derivative is kind of like a best linear approximation, right? So this tells me, what is the best linear approximation of my function if I was to vary it kind of in this direction. And last time what we did is we defined this Jacobian, where we said, okay, let's kind of write down this linear function, which gives you a best linear approximation kind of going in any direction, right? Just by saying, okay, if I go in this direction, what's the best linear approximation? If I go in this other direction, what's the best linear approximation? And build a linear map out of that. Okay, that's what we did last time. But now we're going to, we're actually going to stick to something like this. We're not going to talk about Jacobians, because we're going to talk about a different kind of vector space. So, in the case of a Jacobian, in the case of a Jacobian, that was for maps between what? That was for maps between, yes, Rn and Rm. Okay. But, okay, we will not be looking at Rn and Rm because those are very nice and finite dimensional, but so on and so forth. So there you can write down an explicit matrix, right? Because you have finitely made directions. But now we will want to look at something a little bit more complicated. And now we're going to look at this idea of a functional, which is really the exact same idea. So what we're going to do is we're going to look at the kind of particular case of this, where we're going to look at, sorry, let me see, do I have, yes I do. Just in case, I'll open it for myself so I don't accidentally make a mistake. Yeah. Yeah. So we're going to have the following definition. Okay. So. Okay. A functional is some map let's say what does he call it? Let's call it F, capital F, which, or sorry, is it capital F? Yeah. It's a map which takes in some function space and outputs, say a real number. Could be a complex number, doesn't matter. So why is this similar to kind of the setup we had before? Because if I have a function space, so by a function space I mean just some space of functions. It's some vector space of functions, right? And a function space is, if you have some functions, it always makes, if you have some functions, say functions that go from somewhere into R, right? Then it always makes sense to add functions. right? Because you can just add their outputs. Doesn't even matter what their inputs are, as long as you have a linear structure on the target, you can add these functions. Does that kind of make sense? If you have two functions going from literally any set into, say, a vector space, and then from any other set into, if you have two functions going from the same set into a vector space, then it makes sense to add these functions. Think about that. Does that make sense? Because you just add their output at every point, and addition is well defined. So the space of some functions that have output in R is itself a vector space. Yes, because you can add stuff, you can multiply it by numbers. All of that's well defined. Yes. Okay. So now to say that a functional is something that takes in a function and outputs a number. Right? So, and this is not surprising. Like, for example, think of linear functionals, right, that you've studied so much in linear algebra. If you have a linear functional that takes in a vector, outputs a number, right? Now our vectors are functions, okay, and it outputs a number, okay?
So functionals are elements of the dual space.
So no, functionals are. This is not necessarily a linear functional. I mean, any functional. So it's just something that takes in a function and gives you back a number. That's it. There's nothing more complicated. Okay, so the one example that Arnold gives is the length of a curve. Let's say, I don't know. That's an example. Sure, let's write this example down. So suppose you had a curve gamma. So example. A curve is what? A curve is a function from the unit interval into some space, right? So let's say, I don't know, R2. Then, in that case, f of gamma, so the length of this curve, I think this is correct, is, okay, from T1 to T, well, let's say from 0 to 1. 0 to 1 square root of 1 plus gamma dot norm squared dt, something like this, right? Tx, x of t equals x, yes. Yeah. So, this is an example of a functional. It takes in a function as input and outputs you a number.
Functions from which space to which space, I should ask.
So, I don't know, any space you like as long as it's into a vector space. So in this case, gamma, so for this particular example, gamma is a function from the unit interval into R2. Right? So this took in a function and spit out a number. Or actually, no. Gamma is a function from 0, 1 into, into R2. Yeah, I think that's fine. Yeah. Good. So, I think this formula is correct. Okay, but let's look at a simpler example even, right? So, a very simple example. A very simple example is kind of doing what we just did. You take your function, so it takes in some function f, and we'll just integrate it from 0 to 1. Right? This is a functional, right? It takes in a function, outputs you a number. And this is where f is from R to R. Do you agree? So, you took in a function, you spit out a number. In fact, there's another thing you could define. You could say, let phi, so choose some function g, choose g, and define the following functional, which is the integral from some bound to some bound of f times g bar, let's say. Okay, this would be a functional. I'm assuming here that f and g are functions that have complex output, and so then this functional would be outputting complex things. And this is something that we will see in quantum mechanics the next week. We'll see this kind of functional appear as an inner product, actually. This actually very much looks like an inner product between functions, and this in fact does define one. And so then we'll maybe see what functions do we need to add to our space to make it complete, make it into a complete Hilbert space. And that will also be an interesting question. Okay, but do people understand overall the idea of a functional? You take a function, you give me a number. Okay, that's it. That's it. Doesn't have to be linear. Just function out this number. Okay.
That integral on the bottom,
Yeah.
that's not necessarily an integral over the reals.
No, this is f and g are f(g) are from reals into complex. So it's an integral over the reals.
Okay.
The output's just complex, but sure, I can still do Riemann sums.
Yeah.
With complex numbers, no problem.
Okay, but the domain is the reals.
The domain of f and g is the reals. The domain of the functional, takes in as I put f. The domain of the functional is functions which are integrable in this way, such that this makes sense, and this is finite and whatnot.
Oh, okay.
Yeah. So I'm saying let's fix some g, then you can define something like this. Okay. Good. So now, what am I going to do? No, a linear function we know, that's boring. Yeah. What are we going to do? Connect the dots. There's two things written on here. Hmm? Exactly. So we're going to do something that's like a derivative on here. Okay. So we're going to define okay. So I'll be a little bit unclear, but hopefully it will make sense. So, definition. We say a functional phi is differentiable if so differentiable, say, at gamma in our function space. If what? If phi of gamma plus h minus phi of gamma is equal to what? Is equal to f of h plus some r of h where f depends on h linearly Okay. And R is, of some higher order, so it's not linear. Okay. And the next bit is that we call F the variation of phi. Yeah. I guess not gamma or whatever it is. Okay. So why does this make complete sense? Let me rewrite this.
F and R are functions themselves, right?
Yes, yes. So gamma is some function, H is some function, and I can plug them into my functional. Okay? And so I'm saying let's fix gamma. That's the point that so the previous picture with the vector space that we had. You had a point. You had some point v naught. Now this point is gamma, and I'm saying let's choose some other function h. Some other function h which points in some direction. H, and now let's differentiate in that direction. Okay. And what we said before we said the derivative has to be the best linear approximation in this direction. Do you agree? So now I'm saying that, hey, so what's the best linear approximation in this direction? F is this best linear approximation in the direction of h, right? If you start at gamma and go a little bit and go like to h in the direction h, right? And subtract back where you started from, right? Then this difference, linearly, the best linear approximation should exist and be some linear functional f of h. Okay, and then you have some higher order bit.
When you say f depends on h linearly, does that
Yes.
mean f is linear? Sorry, does that mean f itself is linear? Or
In h. It's a linear functional of h. So it takes in function as input and is linear. So,
What
if
does
I had...
of h mean?
Pardon?
What does of h mean?
It takes h as input. So if you fix gamma and vary h, then this is equal to that. And it is a function of h. As a function of h.
Okay, sure.
So I'm saying you are at a fixed point gamma, this is fixed. Okay, and suppose I choose this h, right? Then f of this h will give a best linear approximation going this way. If I chose a different f of h prime, say this way, right? Then I would plug in h prime and still get the best linear approximation from that. So this is like a Jacobian, but now our vector space is some function space which is infinite dimensional. Yes?
Do we have some kind of restriction on R, similar to one dimension? Because when we did the one-dimensional derivative, like we had the error term is in little o h.
Yeah, so R of h should be of order h squared or higher. So, like one way you could maybe think about this is, if this is a really nice functional, then maybe you can write a Taylor series for it or something in terms of the functions, and then do something that way, and then like this would not have a linear part to it.
Does it make sense to say R of h over something goes to 0?
R of h over something? Not necessarily. No. Well, I guess you could. You could do like, you could say, let's take, so what I'm trying to do here with this definition, I'm trying to define something that's like the Jacobian. So here I can plug in any h, right? This is not a derivative in some direction. This gives me like what the derivative is in any possible direction depending on what I plug into it. If you chose a particular direction, h, then you can literally do that again, where you multiply h by epsilon and then take a limit.
What does higher order mean? If we can't write
So-
it as some limit
Right,
and
right.
it goes to 0 as h approaches 0. I don't even know what approaching 0 means for a functional for a function.
Sorry. Oh, well, okay, true. You don't. So, actually, wait. Let's see. Oh, it does explain, in the sense that. Okay. They define it as follows. So they say that R. And R of H is of order H squared, meaning, actually the book defines this rigorously, I missed this part, that if H is less than epsilon and the derivative of H with respect to whatever argument it has is also less than epsilon, then that implies that R R is less than some constant times epsilon squared, which makes sense.
What do those absolute what's the metric you're using?
The values of the function, of the functional.
Okay, so
This is a number. I can take an absolute value of a number.
well, okay, but you say H is less than epsilon.
Okay, on some region it's a function that's less than epsilon, it's bounded.
At all points?
Yeah.
Okay.
Sure, let's take something like that in the HDT. That could work. Maybe you could define some norms for it, but it will most likely turn out to be equivalent. Yeah. Sure, it goes quadratically with H, right? Because H is less than epsilon squared, meaning that R of H has to be less than some constant times epsilon squared. Okay. But do people see this idea that we can look at the variation of a functional, which is like a best linear approximation of said functional? Does that make sense? No?
Why is there an epsilon squared?
Here?
How does that? Yeah.
Well, because if H is less than epsilon, right? And then the derivative is always less than epsilon, then if you're kind of going away, you can't go. If you go epsilon away, sorry. Yeah, if you travel. Sorry, this is just the condition for being of order epsilons of order H squared for R to be of order H squared, right? So you're saying that if H is very small, like epsilon, then R of H has to be less than H squared in some sense, which is epsilon. Right? If you're saying that H is somehow like epsilon large, right? And you're saying you want R to be of order epsilon squared, then you want to write down something that is like, oh, R of H is somehow less than C times H squared, but that doesn't make sense because R of H is a number and H is a function. So you come up with these conditions. You bound H and dHdt, and then you say that okay, this bound we want this bound to be kind of like this. So this bound is mimicking the idea that you want R of H to be smaller than CH squared, right? That's the usual sense, but this doesn't make sense because this is a function, this is a number. Okay, so you say, okay, if my function was bounded by epsilon, then okay, I can bound it like this. That's the idea. This part isn't quite correct to say. So this is what it means for R of H to be of order H squared. Right? So if H is less than epsilon, then R of H has to be less than epsilon squared. And go like epsilon squared. Yeah? That kind of makes sense? This is like by analogy with just usual functions and usual calculus that you have. Something is of order x squared, right? If it's small, then that function is less than c times x squared, right? So same idea. Okay, but do people see what the variation of phi is? Yes? It's some kind of linear approximation to phi at this point. if you were to start at this point and go in h, how much do you change in a linear sense? Okay, so this is what we call a variation of phi. Okay. Huh. So now, okay, this is fine, yes? Okay, I will now erase this portion. So now, we're going to look at the following functional. Let's define. So, so our space of functions is, functions x that go from the real numbers into, I don't know, Rn, let's say, Rn. And now define the following functional. Define phi of x. So x is this function, equals the integral from some fixed t1 to t2 of some other functional x dot t dt. Okay. So let's think about this for a second. I have a functional L that takes in as input x, something called x dot, and something called t, right? So the functional L actually takes in multiple things, right? It takes in a function x, it takes in a function x dot, and it takes in a function t. So it takes in three things. Do you agree? And now I'm saying, let's plug into L. Let's plug into it x, its derivative, and time. So I'm saying let's plug into L x of t. Let's plug in the derivative of x in here, and then let's plug in t into L. Right? L itself is something that takes in as input, a function, another function, and some number. Okay. Okay, and it outputs number. Okay. I have this function. Okay, it takes in this, and this. Then I say, okay, let's plug. If I have a x of t, which is really, this is also some kind of path. When I like this x, you should really think of it as like the trajectory of something in space. Right? That's what it's physically going to be in the end. Okay? So I can, if I have some path, I can plug it into the values of x of t, its derivative, and t into this function L. And then I can integrate that from some fixed time t1 to some fixed time t2. Yeah? That makes sense. So what I did is I took a function, x, some path x, I plug it into this thing and I get out a number. Okay? That makes sense. And this is a very important example, because this is what we're going to be, we're going to use this to reformulate classical mechanics in a moment. But first, we are going to do the following thing. We're going to show that, so we're going to differentiate this. We're going to say, okay, actually, what's the derivative of this first? And then we're going to talk about classical mechanics, okay? So, let's see. So let's compute the derivative, right? So what is L? L on its own, this is just a function of 3 entries, right? This is maybe a vector, this is maybe a vector, and this is a number, right? So it's a function, L is just some function of 3 inputs, right? But if I plug stuff into it, which is kind of associated with some path, then this whole thing becomes a function, yes? Yeah, so actually, so it doesn't, L doesn't take a function. This really takes in like vector number. Okay, and outputs a number. So L is really just a function. We know how to work with those, right? Yes? Okay. So now let's compute the variation of this. So compute variation. Let me maybe change colors. Actually, no. I'll keep using chalk. White chalk. Compute variation of phi of x. Okay. So what's the variation? Variation. What did we say? We wanted to look at f of x plus some other path h. I add some little path h to it. Subtract phi of x, and then try and find the linear approximation to this. Okay. So we're starting at some point x, and I'm saying if I add a little path to it, like perturb my path a little bit, then what is h, right? So what's the picture? The picture is I have some kind of path that's parameterized by t. So it starts at t1 here, ends at t2 here, right? And I'm saying let's add a little h to it, which is which is kind of the same path. H will be like a little deviation. So x plus h will kind of follow the same thing, but maybe there will be some little differences. So this is x plus h, and then this is x. Okay, so this is they are functions of t. So this should really be x of t1. This should be x of t2. This should be x plus h of t also. And so white should just be x of t. Okay, do people understand what everything is? X of t is a path, right, in Rn. H is also a path in Rn, but I'm saying that H is like a path that is like very close to the origin. So if I add it to something else, it doesn't change it by too much. Okay?
Because x and h are now outputting vectors of Rn, it's not elements of R. How does the less than epsilon work? Is it just all the entries of the vector are less than epsilon?
Pick your favorite norm. It doesn't matter.
Okay.
So you can do like coordinates squared and then square root.
Okay.
Which is, you take that from the inner product. Let's say that's the Euclidean inner product. Or you could do that, what you said. All of them give you the exact same thing. So if you have norms on a finite dimensional vector space, all of them give you the same topology. So you'll just have some extra factors of like 1/2 or something in your calculation or whatever else. Your bounds will look different, but at the end of the day, everything will work out in a similar way. Okay. But yes, good question. Yeah. Okay. So let's just explicitly compute this, right? So this is t1 to t2. Let's just plug this in to all of this, right? L of x of t plus h of t. X dot of t plus h dot of t. So when I say h dot, I mean a derivative of each component with respect to time. Right? People remember, if I have a function that's a vector, I take the derivative of it with respect to, if I have a function that takes in one input, outputs a vector, then I can take the derivative by taking the derivative of each entry. Yes? And that would give us the best linear approximation. Okay. So this is t dt, and then I want to subtract from this minus, okay, t1, t2, L, x of t, x dot of t, t. Right? People agree with this, yes? Very, very easy. Now, how are we going to do this? We are going to use we're going to use just kind of regular calculus, right? How are we going to do this? Okay, well, if this was just a function of, x, some other variable x dot, and some other variable t, right? What would be the best linear approximation to this? If this was so, forget about the fact that these are functions and whatever. L is just a function that takes in like some vector, some other vector, some t. What's the best linear approximation to L? So L is a function that takes in a few vectors as input, outputs a number. Yeah, so I want to take like the usual Jacobian, the usual derivatives, right? So let me see what's the best way to write this down so it's not completely confusing. So, okay. I will rewrite this in a slightly more, in a larger way maybe. Let me see if this, is this what I want to write? Because this notation is a little bit unclear in my opinion. Actually, yeah, let's keep using this notation. Okay. Yeah, I'll keep using this notation. So I just want to take the Jacobian. But I'll do this in a very particular way. I'll first say, okay, let's fix these guys. Let's fix this. And kind of take a derivative in these entries first. And so kind of look at the part of the Jacobian that only takes the input vectors like from the first entry. Right? Then look at separately at the Jacobian which fixes this and kind of takes the inputs in here. Okay. So this is going to be what? We'll write it in a very suggestive way. We'll write it as, so I have t1 to t2. So this difference should be what? It should be the derivative of L with respect to x times h, right? Plus the derivative of L, L with respect to x dot times h. And we also need a, oh, we don't need anything else. Yes, that's right. dt. And we're going to have some, something of higher order. Oops, r of h squared, but okay, we ignore it. Because I just wanted to compute the variation. I wanted to compute the linear approximation. Okay. Now you might be asking, what is this and what is that? Right? Good question. Yes. Do you understand why it's unclear what this is and what that is? Why is it unclear what this is?
can you differentiate it with respect to a
Vector, right? Because x is a vector.
Okay, that makes sense.
X is a vector, right? So why is this unclear? So okay, so suppose x was a function that takes in r and outputs just one number, right? Just not a vector, just one number, right? Then, so L is what? L is then a function of x, y, and I don't know, z, right? X, y, z. And in here, I'll just, instead of x, I plug in x, well, that x, I plug in x dot here and t in here. Do you agree? But okay, if I wanted to look at the approximation of this, right? So if I wanted to take the derivative of this with respect to something, oh wait, this has to have an h dot here. Is that right? Yes. Yeah. So let's look at it this way. Why does this have to be equal to that? Actually, no. I'll write up here. It has to be equal to that because. So suppose these were just numbers. So L took x, y, z as numbers, right? Okay. Suppose I did L of x plus some h, where h is like a number, no longer function. Y, z, right? And did minus L of x, y, z. Okay. Well then, of course, to first order, this is going to be what? This is going to be partial L, partial x, right? Because that's just the first entry, evaluated at, okay, let's say, call this x naught. Evaluated at x naught times h. Well, at x naught, y, z. Right?
Yeah, we're ignoring the error term.
Yes, if you ignore the error term. So, plus O of h squared. Do you agree? So this is what would be if all of these were just numbers. Do you agree? You look still confused. Okay, but does this part make sense? Okay. And then, okay, if I added something else to y, right? I added some other bit, so plus, I don't know, some other h squiggle, so maybe completely unrelated to this h, just another letter, right? Then what would I do? I just differentiate kind of in the direction of h squiggle, and add in a term here. I'll do dl dy evaluated, okay, skip this and all. Evaluated at x naught, y naught, z naught, right? Times h squiggle. And then, okay, then I'll have a remainder of order h squared. Okay?
Is it just h squared, or is it h squared times h squiggle squared?
What do you mean? Sorry, say that again.
Like,
oh, order something, okay, something that is quadratic. Okay, you're going to have, okay, it's going to be
Okay.
quadratic in like both of them, in terms of both of them. Okay. Yeah. Does that make sense? Okay. Now, in our particular case, it just so happens, so this is, this is your x, y, z, right? When I write partial L, partial x, right? Now I'm kind of making it being a bit unclear. See how there are x, y, z, and the second derivative I took with respect to y, right? Here, instead of rewriting like x, y, z, I'm lazy, and so I just call the second variable x dot, like call something x dot without by assuming like x dot is like separate from x. So when I say partial x dot, I mean take the derivative with respect to whatever you put into the second entry. So this is like partial x, partial y. Partial L, partial y. Yes? So so if these were all numbers, do you see how, okay, I took what I wrote there, which we all agreed with, and I just, instead of plugging in h and h squiggle, I plugged h instead of h, and h dot instead of h squiggle. So this is like partial y because I'm taking the derivative in the second entry. If this was x, y, z. But usually people abuse notation. Instead of writing partial y to mean the derivative with respect to the thing in the second entry, people say, well, the thing I put in the second entry is always x dot, and so let's think of x dot as like its own variable. Okay, when in reality what we're plugging in is the derivative of x. Okay. Does that make sense? And so this is then the variation of f.
What? When we're taking a partial with respect to x dot, like, isn't that in terms of x somehow?
No. Look, replace x dot with y. Does that change anything? The function L has 3 inputs, and I'm taking a derivative with respect to whatever the second input is.
Okay, sure.
Right? And that has nothing to do with what the input actually is. Right?
Sure.
That's just, I stand here and I differentiate in all directions, and only then do I realize, oh, I'm plugging in something that's a derivative of x in here. Okay, and so then you plug in h dot.
Oh, okay, because it's h dot over there.
So, okay, like I'm just write y instead of x dot.
Okay. Makes sense now.
Instead of x dot, like when I write x dot in this context, so here when I write x dot, I mean literally the derivative of x. Here when I say derivative with respect to x dot, I mean derivative with respect to the second thing you plug into L. So derivative of L with respect to the second entry. Okay. Yes? Kind of? Makes sense. A little bit. So for now, let's think of x as a function into a single output is a single variable. So not a path in Rn, but a path in just R. Okay. But if this was a path in Rn, then you could still understand that, okay, this would be some Jacobian that you kind of vary everything in these entries, and then look at the function, the output you get. Okay, but we'll maybe look at examples in a moment. Okay. So in this case, you get that the variation of this kind of thing looks like this. You take a derivative of L in the first entry, multiplied by the little thing you add. You take a derivative of L in the second entry and multiply by h dot of the thing you add, and so that way you get the derivative. Okay, so one thing that we need to check is this indeed linear in h, right? Okay, well this part doesn't depend on h at all because I'm just taking a derivative of a function, right? Doesn't have anything. Times h, multiplying by h is always linear. Right? Multiplying by the derivative of h is also always linear because taking the derivative of h is linear, and then adding something to h is that's also linear. Yes. So this is indeed the linear approximation that we were searching for this kind of functional. Okay. Okay. Good. So this is, you're right, this is the part that confuses people. That in different points of the calculation, people write x dot sometimes to mean the derivative of some function x of t, and in other times when people write x dot, they don't mean actually a derivative of the function x, they just mean the second entry into this function L. And that's what causes a lot of confusion. And that is what caused me a lot of confusion, because I was asking the same question, but wait, isn't x dot the derivative of something? It's like, if you abuse notation, then it's not. If you, in some contexts, x dot is just the second input, and in other contexts, x dot is the derivative of x. But we will see why this is, in fact, the convenient thing to write in a bit. It looked like you're about to ask a question.
Why is
True. Because if you know h, then you know h dot because you can differentiate. Right? So it only really depends on. Oh well, sure. You're right. I can do h dot squared. But that's why in the condition before, for defining what it means to be of second order, we bounded h by epsilon, and then we bounded h dot by epsilon as well.
So
Remember?
it's unnecessary to write h dots.
Hmm?
So it's unnecessary to write h
No,
dots.
no, no. Actually, maybe it is. Maybe it is necessary. Maybe you should.
We also need to bound h dot by epsilon and h double dot by epsilon because
Well, you don't need to bound it. Like, it's like that. What I wrote there was defining what it means for r to be of order h squared. Is if you were to bound h by epsilon and h dot by epsilon, then r would be bounded by epsilon squared. That was the definition of what r is. Like of condition r has to satisfy for it to be of order epsilon squared.
and in this case if h dot is less than epsilon squared and h double dot is less than epsilon squared, then
Not
it's
double
fine.
dot. There's.
Because it's also order h dots.
Oh no. Yeah. So with this, you want this to be of order epsilon of order h squared, not of order h dot squared.
Then why is h dot?
Because you input like okay sure. The point I'm trying to make is that it's not. It's. Actually, yeah. You know what? Yeah, that's fine. You're right. Sure. That's fine. Yes. You know, this is the part that I'm not interested in. I'm interested in this one. Okay? As long as you understand how we arrived at this. But all I did is, you know, if I'm adding a little h into the first entry, that means I take a derivative in the first entry, multiply it by h. If I am adding a little h dot into the second entry, that means I take a derivative in the second entry, multiply it by h dot. That's all I did. I took a derivative twice. Like a usual one-dimensional derivative that you know how to do. Yeah? So this makes sense. Okay. Okay. So now we're going to talk about classical mechanics. Let me see. Do I have a copy of Landau here? Landau mechanics. I do. Oh, it's in English. Horrible. Okay, that's fine. So don't worry. We will talk about this again and again next time, and so on and so forth. I'll spend some time on this. Okay. Okay. Can I erase this? So okay, suppose we're doing mechanics over Rn. So the configuration space is Rn. My particle for now let's stick to Rn. Okay. So my particle or number of maybe multiple particles, their position is somehow specified by n numbers. Okay? Good. Then okay. Then I want to specify their, so if I have a like some particles at various points, so maybe actually let's say there should be 3n, where n is the number of particles that I'm describing. Do you agree? This is something that we'd give in Cartesian coordinates, right? Then, if I wanted to, I also need to specify their velocities. Okay. And so, okay, we can. Yes. Okay. We can specify their velocities. Okay. This is also some really big vector in r to the 3 to the n, right? So I give a velocity to every single particle, right? There's n particles, so there's the velocity has 3 components, x, y, z, and so okay, that's also in Rn. Okay. Okay. Now, right. Now I'm going to say actually, this is if it was in Rn, and this is like, okay, if I was choosing usual coordinates, right, for my particles, right? But perhaps I don't need as many coordinates as 3 to the n. Because suppose I had my particles restricted on some ring, let's say, right? I had like 2 particles on a ring, and this ring was fixed. Do then I need 6 coordinates to tell you where these 2 particles are? No, I only need 2 coordinates. I only need to tell you, say the angle this one makes with this, and the angle this one makes with this, right? That's all I need to tell you. So in fact, we'll define generalized coordinates. So Q in some r to whatever, so r to the m is for now it's r to the m, later we'll switch around what this is. Generalized coordinate. And what I can do, so I'm saying that Q is a generalized coordinate if I can somehow use Q to specify the position of my system in my configuration space, whatever it may be. So Q is some coordinate telling me where all of my particles are at. Right? And I'm just saying it doesn't have to be the usual x, y, z coordinates, right? If I wanted to, I could use spherical or polar coordinates or whatever it was, as long as I can use Q to somehow specify the position of my particle, that's fine. Okay? Does that vaguely make sense? Okay. Yes. So in fact, yeah. So so any Q1 up to Qn. So where so this was a vector. Now these are just numbers. So R or Qm are generalized coordinates. If you can use them to specify the position of all the particles. Okay? That's fine. Okay. And so derivatives Q dot I are called generalized velocities. Why is this generalized? Because maybe if you take Q dot and then square all of them, they might not give you the actual speed at which the particle's moving. It would actually give you the velocity, but okay, you can maybe use this to figure out what the velocity is in like Rn or whatever your particle is moving. Okay, So I'm going to define q1 up to qm, generalized coordinates, if I can use these numbers to specify where all of my particles are at. And their derivatives, qi dots, we'll call them generalized velocities. Okay? Yes? Makes sense. So, I can't move this board. I will erase this. Yes? That's fine. Is the video visible? Yeah. Is my mic still green? Is it still shining green?
Yeah.
So now, let's look at, so how are we going to actually do classical mechanics now? So we're going to do the following. So we're going to look at the principle of least action. Okay. And the principle of least action goes as follows. So let me see. How does he phrase it? Yeah. So any mechanical system, so this is kind of our postulate. Any mechanical system is characterized or fully described by some function called the Lagrangian. Called the Lagrangian, which has the following inputs. Okay, so it has, so right now, be very careful. Right now when I write q1 dot, whatever qm dot, I don't mean a derivative of something. Right now, this means, like the thing I put in this entry. So right now, think of q1 dot as like y, z, or whatever, just a symbol. Okay. Don't think right now. Here, I'm just saying q1 up to qm, because later I will plug in the derivative of q1 dot into here. But as far as you're concerned, right now, this is just like the n plus first entry, the thing I put in the n plus first entry. Okay. And usually people don't write all of this because this is very long. Usually people just write q dot t and think of q and q dot as some vector. Okay? So I'm saying that everything there is to know about some physical system is somehow encapsulated in some function L, in some Lagrangian. And this Lagrangian takes in 2m inputs and then another one. Okay, it's just some function which takes a bunch of inputs. Okay, whatever. So now the question is, how do I actually figure out, what is my motion of my particles in my system, right? So I want to see how do my generalized coordinates change with time. Okay. Yes. So for this case, we define the action. So the action is it's this functional s, so s of q, where I take the integral of the Lagrangian. Okay, and now when I write q dot, I actually mean the derivative of q as a function of time. Okay? So if I want to find how my system evolves over time, that is the same thing as saying I want to figure out what q of t is. So I want to figure out what is the position of my particles at every moment in time. Yes? Because the generalized coordinates tell you the position of your particle in some way, shape, or form. Okay? Okay. Does this make sense? Okay. And now, so I told you that, okay, this Lagrangian is somehow fully specifies everything, right? Okay, so now I need to tell you how to actually get what Q should be out of this Lagrangian. Like if I gave you a Lagrangian, how do you figure out how my particles should evolve over time? Okay, so so the action is this. So the action, notice the action is some functional, right? It takes in Q, it outputs you a number. Yes? So now, the motion of the system is then given by some function q of t such that what? Yeah. What? So here when I say q of t, I mean I plug like the thing I plug into S.
Okay.
So here I say that the motion of function is given by some function q of t, which satisfies the property that if you were to take the such that the variation of S at q of t is 0. So I'll write it like this. The variation of S evaluated at q of t is the 0 linear function. So by del S, I mean so the variation, so like the derivative of the functional. So I'm lazy. So remember how we had like phi of gamma plus h minus phi of gamma, or I use x, right? X is equal to like f plus r, right? Of h and of h squared, right? Remember how we had this? And we called this the variation. Now instead of writing f of h, I'm going to write delta of f. So it's, I mean, the variation of phi at x. Right? So I'm just saying derivative of phi at x, essentially. Okay. Okay, and this function is fully determined by the initial conditions of what the positions and speeds of all of my particles are at the initial time. That's enough to fully specify all of this. Let's see. Let me see.
Is the remainder also 0, or is it just?
I'm just the variation is 0. So to first order, so the idea is that if it's a particular path, right? this particular path in my space, such that if I was to plug it into L, right, and maybe perturb this path a little bit, change it around a little bit, then to first order it's not going to change at all. So it's somehow in this equilibrium position where if you change the path a little bit, this quantity doesn't change by much. So let me see. Does it say? Yes. And and you want at the initial time t1, q of t satisfies some initial condition. Okay. So the idea goes as follows. The principle of least action says if I have any mechanical system, actually maybe let's wait for Trevor, I don't know. If I have any mechanical system, then there has to exist some Lagrangian function associated with it. And from this Lagrangian function, if I know the initial state of my system, of like where all the particles are and what all of their initial velocities are, then from that and this Lagrangian function, I can figure out what the I can figure out how the system will evolve in the future. Okay, and the rule for how to figure it out is you want to find a function q such that if you take a variation at that point, so like if you take a derivative of this functional at that point, then you get 0. Meaning that if I was to change so the ideal path is the path that if you were to change it a little bit, it wouldn't change this quantity too much. So, let's maybe draw a picture. What are we really doing? So let me see. I'll redraw over this picture. No, you also want a boundary condition on the edge. So satisfy some initial condition at times t1 and t2 satisfies some initial condition q of t1 is equal to some q1 and q of t2 is equal to some q2 and q dot of t1 is equal to some q1 dot and q of t2 is equal to some q dot. Okay. So it was a bit imprecise. Yes. Yeah, so I'm going to say it again. So the principle of least action says the following. That, if you have some mechanical system, right, we're saying that, so before we said that, I can use some generalized coordinates to specify where all of my particles in my system are. And let's call q dot the derivatives of q to be the generalized velocities. Okay. Now I'm saying that if I have any mechanical system with some coordinates, the generalized coordinates q1 up to qi, then it has to be fully characterized by this function by some function that's going to be called the Lagrangian. This function takes m plus m and then t inputs, so 2m plus 1 inputs, potentially. And then I say, now let's define this functional called the action. And I'm telling you that the Yes, and then they say, suppose I have these initial conditions and initial and final conditions. So suppose I know that my system at the beginning starts at these points with these velocities, and at the end is going to have some points and it is going to end up at another point with some specific velocities. Right. So suppose this is also given. Right. So you know how your system starts off and where it ends. Then the path that the system is going to take, this path Q of t, is going to be the path such that if you were to take the derivative of this functional at this path, you get 0. Meaning what? So let's draw a picture. I have my coordinate axes, right? And suppose that I know that my system has to start at some point Q1 here and end at some point Q2 here, and initially it has to have some velocity Q1 dot, and here it has to have some initial velocity Q2 dot. Okay? Suppose I can suppose we know this, right? So like in first year of physics, you have like, let's drop a ball from the top of a mountain kind of thing, right? Suppose you know that. And it has to end up at the bottom of the mountain. Okay. Make sense? So then I'm saying, okay, let's look at all the possible paths I could draw. Right? I could draw so many paths that connect these 2 points, right? I can go, maybe my particle goes like that. Or maybe, that's fine. Like that. Or maybe it goes like that. Sure, like 2 possible paths. Right? I'm saying now, okay, hold on. Let's not, of course, not every path is going to be allowed. So let's define this thing, which is going to take in a path and output a number. Okay? And so now we can look at all possible paths, plug them into this, and see what we get, right? And then I'm saying, okay, let's choose the path, the one good path, the one path that if you were to perturb this path a little bit, get something like this, right? Then that practically wouldn't change this value at all.
How do you know it's unique?
Great question. So that's why, if you know the Lagrangian, then you can show, like if you know what the Lagrangian is, then you can show, for nice enough Lagrangians, you can show that then motion has to be unique. But in general, maybe you can couple Lagrangian where there's multiple nice paths. Yes, and in fact, that is true. Like if you can write down Lagrangians very easily, which give you, which actually have like infinitely many paths that satisfy this condition. I'll give you an example of a Lagrangian, maybe such a Lagrangian, maybe next time. Okay? But do people see this setup? You have some Lagrangian function. From that Lagrangian function, you build a functional, right? You have this functional. And you want to pick a function such that if you plug it into the functional and perturb it a little bit, then this to linear order doesn't change too much. Okay. So you're right to be looking at this board now. Remember, we computed that del S for that kind of thing is this thing. This is in fact del S. Do you agree? Okay. So now we actually have a very concrete thing. You want a function such that this quantity, which you can explicitly compute by hand, is 0. Right?
That looks like a lot of work.
It's not.
Okay.
We will simplify this in a second. by recalling that you have this wonderful thing called integration by parts. And we will reduce this to essentially solving some ODEs. Okay. And yeah, let's do that now. And then we'll stop. And then maybe on the homework I'll give some examples, and then we'll discuss, we'll actually look at examples next time. Because right now this is a bit maybe not entirely clear. And that's okay. That's supposed to be like that. Okay. Yes, but people understand the principle of least action. So why is it called the principle of least action? Right? Because, so this is the action, and we're trying to find a path such that the derivative is 0. So that's kind of like finding a minimum. Now, this does not actually mean, this might not actually be at a minimum. This might be at just any extremum. Right? Like you could have like if you think incorrectly about thinking this as like a function of R3 instead of an actual functional, right? You can have something where the derivative is 0, but it's not a minimum or a maximum or anything. So some people call it the path of least action. Others call it like the something with like extremum or whatever. But yeah, I think the more right way to think about it is in terms of an extremum. You want to find a particular path such that if you change the path a little bit, this function doesn't really change, at least to first order. Okay. So now let's actually compute this. Right, so our function we had S is equal to integral T1, T2, Lagrangian of Q1 up to Qn, Q1 dot up to Qn dot T, dt, and this was a functional S, oh, my bad, which takes Q of T as input. Okay, and so we wanted to find Q such that what? Such that the variation of S at Q of T was 0. So if you change around Q of T, this integral thing does not change by much. In some sense. Okay. So we computed just before. So now just replace phi with S and X with Q, and the formula is the same. That del S is, the variation is, you take the derivative of L with respect to Q, and multiply it by the little change we make. So so let's call, instead of H, so I'm going to, instead of X I'm going to write Q. Instead of H I'm going to write delta Q. So think of del Q as like a function. So del Q, like this is one symbol together, and that's like just instead of H I write that now. Okay, it's just convention. Okay. So by little delta Q. Okay. And now have partial L, partial Q dot. L Q like dot of this thing. Okay. So small thing. Actually, let me rewrite this to make it more clear. Because now, so see, before I was writing this as like this thing of vectors, let's make it even more clear. Let's take a sum over I equals 1 to n, qi, qi, plus sum I equals 1 to n qi qi. Why? What am I doing? I have n entries, and so I just differentiate in each of those entries, right? So instead of writing, see here I was writing this as like a vector or whatever, right? I can always think of as a vector as a bunch of like numbers, right? As an n-dimensional vector is n numbers, and so that I can just, now that I have everything in n numbers, I can just differentiate everything with respect to each entry, and then multiply by the little change that I've made in that particular entry. So that formula is the same as what I wrote down. Okay.
Why don't the partial QIs cancel out?
What do you mean?
Like, I have partial QI in the denominator and then I'm multiplying by partial.
Okay, this is a derivative.
Yes.
And this partial QI means that I'm taking the derivative with respect to this entry.
Yeah, yeah.
Right?
Okay.
Del QI is not partial. This is an arbitrary function that I added. When I write this QI, I just mean this entry. I take a derivative
Yeah.
with respect to this entry or this entry, with respect to some direction. When I write delta QI, I'm saying I'm adding some little function. So del S, remember what del S was. So del S was S of Q plus delta Q minus S of Q. Okay, and so this is like to first order, this is equal. Right, so I'm adding to Q a little function delta Q.
Which isn't actually dependent on Q. It's just small.
Yeah, it's just some arbitrary function.
Okay.
Arbitrary function not dependent on Q. Okay. And when I write QI as when I take, let's say I take a derivative with respect to QI, I don't say I'm taking a derivative with respect to a function, because that doesn't quite make sense in this case. I'm saying I take a derivative of L as a function of some numbers in this entry. So I fix all the other entries, and then I take a derivative with respect to Q1 or Q2 or Q3. And the same thing for partial with respect to Q dot I. I'm saying that I'm taking a derivative with respect to one of these entries, and not these, to just differentiate between these entries versus these entries. Okay? That makes sense? DT. Sorry, is my writing here clear? Let me rewrite this again. This looks ugly. So I'm taking I vary everything in each entry a little bit. So I take the L, the function L, I vary it in the ith entry, and then I multiply it by, how much my entry differs a little bit, right? And then I do the same thing. I vary it in like these dotted entries, dot I. Okay, and multiply it by the derivative of delta Q, because the thing I plug into here is the derivative of delta Q, the thing I plug into here is delta Q. Okay, dt. Okay, now do people remember how to integrate by parts? Have people seen integration by parts? Yes, okay, so you know how to integrate by parts. So let's integrate this term by parts. So I'm going to rewrite this term as before. This is fine. Okay. Now, I'm going to integrate this by parts how? Okay. So this is a derivative of something with respect to time, right? This is not. Okay. So then, if you remember how integration by parts works, integration by parts is what? If you have, if you have u times v prime dx, that is equal to u times v. So at I evaluated, x naught, x1, so depending on what the boundaries here are, right? And subtract u prime v dx. Okay. Do people remember how to prove this in general? Yeah, this is just product rule. Right? If you take a derivative of u times v, right, you get u v prime plus u prime v. And so I just take the derivative of this, and then subtract one term from both sides. Okay. So I'm actually going to write this part first, and then so here I have a derivative of del qi with respect to time, right? So this, the kind of by part, if I integrate this by parts, I'm going to write the second term and then this term and then this term. So I'm going to have d dt, so a total derivative of time now, a total derivative of time, partial L partial qi, right? Times delta qi without the derivative, right? You see how I got here? And then plus, I'm going to have partial L partial qi dot times delta qi. So this the integral ends here. I evaluated t1 to t2. Okay. Do we see how we got here? Maybe.
Yeah.
With some luck. So all I did is I integrated this by parts. That's all I did. So that's why you have a minus here. The time derivative moved onto the delta, onto this derivative term. And yeah, the partial qi is, the del qi is like, that's my function, which I add to q. Okay. Notice that this is a total derivative, not a partial derivative. That's important. Why is it a total derivative? Because, well, when I'm taking the integral, I want to assume that everything could potentially depend on t. Anything that can affect the integral, I want to differentiate with respect to it. Right, this is not a directional derivative. Yeah, okay. So now, let's first look at this term. Right? Let's first look at this term. This term, I said what? I said earlier that I'm looking at paths which kind of start at one endpoint and end at the same endpoint. Sorry, start at an endpoint and end at an endpoint, but these endpoints are specified. So I'm essentially looking at all possible paths, between these 2 points. I don't want to consider paths that don't start here and don't end here. What does this mean? This means that this delta qi term has to be 0 at t1 and t2, right? Because I'm saying, let's take find a q such that if I was to add a little delta q, the variation is 0. But I want to make sure that when I add the delta q, I still satisfy all of my conditions. So this delta q has to go to 0 at t1 and t2. So it's not actually changing anything. It's not changing the endpoints. So this is going to go to 0. So now I'm just left with this. Do you agree? That term went to 0, so.
Maybe.
Sorry, this is summed over.
Can you say again why it goes to 0?
Because I'm looking at paths which start at this point and end at this point. If q is a path that starts at this point and ends at this point, suppose I add a little delta q to it. I want the new path, q plus delta q, to still start at this point and end at this point. And the only way to do that is to enforce and demand that delta qi is 0 at the endpoints. Yeah. So I demand that delta qi is 0 at the endpoints. So this term is 0. Because this is my boundary condition. Okay. Now, let's now put this all back together. Have integral from t1 to t2. I have a sum, n, I equals 1. Okay. Is there anything I can factor out here? Is there anything I can factor out here?
You can move the sum outside and...
No. Factor out.
Delta qi.
Delta qi. There is no dot here. That's it. Just show. Delta qi. I can factor it out. So I can look at minus minus d dt of delta L, delta Qi dot, right? All of this multiplied by my delta Qi. Do you agree? And I sum over all of these. Do you agree?
Yeah.
Okay. Now we're done, essentially. Because let's look at this. What did we want? By the principle of least action, we wanted del S, so we wanted to find a Q such that del S is equal to 0. Yes?
Yeah.
That was the goal. So we wanted to find a Q such that del S is equal to 0. We just further computed del S to be equal to this thing in our particular case. Right? So we added this extra assumption that delta Q has to go to 0 at T1 and T2. This is the physical assumption that we added in, right? And then everything else was just math, like before. And we arrived at this equation. Yes? And now we want to set this to 0. So we want to find a function Q such that you do this, and then this is 0.
For all delta.
For all delta Qi. Exactly. So this is the important part. We want this to be 0 for any possible delta Qi that I could write down. Right? So what does this mean? If I want this to be 0 for any delta Qi that I could possibly write down, what has to be 0? This bit always has to be 0. For every delta Qi. So in fact, for any I, this equation has to be 0. Why is that the case? Suppose that I had something that was, I had a Q such that this expression was non-zero for, say, one of the, this expression was not 0 for one of the, for like one point in time, right? Then I can choose a Qi which is 0 everywhere except for like that little region where this is like non-zero, right? I can specifically choose a Qi around the region where this is non-zero, such that this is like positive in that small region, and then 0 everywhere else, and you will get that you'll just get that this evaluates to something non-zero.
Delta Qi is continuous?
Yeah, sure. Delta Qi. Delta Qi represents me changing my physical path somewhere. Paths in physical space better be continuous. I'd even say they better be differentiable. Surely.
Smooth? Or is that too much?
Yeah. Let's even say it's smooth. That's fine. Because later we're going to want to write this on a manifold, and then you'd want it to be smooth. Right? Because that's why we're choosing generalized coordinates, right? Because you can parameterize your manifold in many different ways. Anyways, so what does this tell me? So do people see why, suppose this was non-zero even anywhere, even a little bit, right? So we're taking an integral over this. Suppose this was non-zero somewhere, right? Anywhere. Then I can choose so it's non-zero at, say, T1. Then I can choose a delta Qi, which is 0 everywhere except for a small region around, T prime. I can choose a delta Qi, which is non-zero, which is 0 everywhere except for a small region around T prime, and get that this integral evaluates to something that's non-zero.
Isn't delta Qi small somehow?
Yeah, sure, it's small. That's fine. It's small, but I can still choose it to be small but non-zero. And then this, I want this to always be identically equal to 0.
Okay.
Not just about 0. I want this to be equal to 0. Yeah. So think about it. Let's draw a picture. Suppose I had a function which was non-zero, say like right here.
Yeah.
Right? I'm saying that I have some function, so something, times delta Qi, and this has to always be 0, right? And I'm saying I can choose what delta qi is. I can choose delta qi to be anything as long as it's small or whatever.
Okay, but small means like less than epsilon.
No. That's no. Just any delta qi. Any delta. I want this to be 0 for any delta qi. Small, not small, doesn't matter. Right? Because remember what the variation was. We wanted the variation to be something linear in delta qi, and it is.
Okay.
Right? So I can choose delta qi to be anything
Okay.
that I want. And so I'm saying that, okay, I want, suppose this function was non-zero like anywhere. Like, there was a patch where it was non-zero here, right? That means I can choose a delta qi, which is 0 everywhere, and then a little bump here, and 0 everywhere. And then this integral will be what? Which will be 0 everywhere, then this multiplied by this here, and then 0 everywhere. So it's going to integrate to something non-zero. So you know that because I have the freedom to choose delta qi to be anything, then each of these terms has to be 0. And also note that I can choose each of the, for any I can choose delta qi to be its own thing, right? I can vary my path in kind of each direction independently of the other directions. And so we get what are called the Euler-Lagrange equations. And this is where we will end. So what you do is you just copy this and you set it to 0. That's what I'm going to do. These are the Euler-Lagrange equations. And the principle of least action gives you the Euler-Lagrange equations. I want to erase this. I guess I can erase this. So Euler-Lagrange. You take a derivative of the Lagrangian with respect to q dot I. So when I say q dot I, remember I'm taking the derivative of L as some function of some variables with respect to the entry in which I plug in q dot I. So this is like a derivative dy, which is I write q dot I to specify a particular production. Okay, so ddt of dl dq dot I minus dl dqi has to be 0. And this has to be true for all of my generalized coordinates. So what I'm doing, yes, and I'm of course evaluating all of these derivatives at q of t, q dot of t, and at t. And this is of course also evaluated at q of t, well, this derivative is evaluated at q of t, q dot of t, t. Okay. Do you agree? So what I do is I take a derivative. So what's happening is I take a derivative of L as if it was just a function of like x, y, z with respect to this entry. Then I plug in q and q dot as like actual functions, and then I take a derivative with respect to time of this as a function of time. Does that make sense? So this is just a derivative of like with respect to some entry. Then I plug all the q as an actual function into there, and then take a derivative with respect to time. Okay, does this make sense?
We know that the sum must be 0. Why does that imply each term must be 0?
Good point. Because I erased it, or was it? Where was it? The sum. No. Did I erase it? Or
It's on the left.
it was on the left backward. Because the sum was 0, but so this term, I multiply each of these terms by a delta qi separately, right? Each of these delta qi's I can vary independently. Delta q1 is not at all related to delta q2, right? I can, on this picture, I can choose a little variation where I give it a little bit of an x component, right? Or I could choose a variation where I can give it a little bit of a y component instead. Or well, left or right, like an up component or a down, I can choose how much I vary stuff in the x direction, independently of how much I perturb stuff a little bit in the y direction. Do you agree? So this means that I can, for example, choose delta q1, delta q2, all of them up until the last one to be 0, and to then only set the last one to be non-zero, right? And then I apply this argument with the little bump. Yes, makes sense? So because I can choose, I can vary each one separately, then, yes. Because I can vary each one separately, each one of the terms has to go to 0.
I didn't see that it was in the sum.
Yeah, this is all in the sum. Yeah. Because it has an I index, so it's in the sum. Okay. So we'll look at one simple example of a Lagrangian, and then we'll go. So we'll look at a Lagrangian of a single particle in one dimension. Simplest thing. 1/2 mx dot squared. Do people know what this is? Kinetic energy. Okay. So this is a particle. So and this is going to be our entire Lagrangian. So this is the particle, which has if there's only a kinetic energy term in here, does this particle interact with anything? No. So this is the Lagrangian for a completely free particle, which doesn't. There's only one particle in our universe, and that's all. That's it. So now, you can actually show by using symmetry arguments that in fact the Lagrangian for a free particle has to be this. But we won't do that now because that takes a while. It's like 2 pages in Landau, so that means it's like 2 hours of descriptions. Okay. So now let's write down the other Lagrange equation for this. Okay. So we have only one dimensional, so this is only one coordinate. There's only one coordinate x. So what's dl dx dot? What is this? So think of x dot as like y. Replace x dot with y. This is just mx dot, correct. Good. What is dl dx? Partial L, partial x. Do you see an x here without an x dot? It's 0. And you don't need to guess. So remember, remember, when I write partial L, partial x, I'm thinking of L as a function of x, y, z, where instead of y, I write x dot.
They are related.
No, but I could. So, okay, let me rewrite this like this. This Lagrangian is equal to 1/2 m y squared.
Yeah, but y is equal to x. Like.
But look, here I'm taking a derivative of the Lagrange of this function with respect to y. This is the formula. The formula is this. It's just that instead of y, I write x dot because I'm abusing notation. The equation was this. Like, y, like,
Okay, sure.
how is y related to x? It's not. It's just that instead of writing y, I'm lazy and I write x dot and to confuse you on purpose. That's all it is. So when I write x dot, I mean take a derivative with respect to the second entry of the Lagrangian. This is the second entry. This is the first entry. This does not depend on this, as far as the Lagrangian is concerned.
Okay.
As far as the Lagrangian is concerned, right?
Sure.
Okay. So this is 0. Now I evaluate it at my path. So now, once I evaluated this at my path, x of t, x dot of t, okay, now this has become a function of time.
Okay.
And this is no longer just a y. So now I've plugged in the path, I've plugged it, evaluated at the path. Now this is a function of time. Before it was just symbols. Now it's a function of time. Okay? So I had this. Okay. So now, what is this saying? This is saying I take the derivative of this with respect to time. I take d dt of, so okay. I have this thing separately. I have this thing separately. Okay, now I just plug all of this into this equation. And I get what? I get the derivative with respect to time of mx dot of t, right? Minus 0 is equal to 0. What's the derivative of mx dot with respect to time?
X double dot.
Yes.
Acceleration.
Yes. So you get mx double dot is equal to 0. Have we seen this before?
Bro.
This is f equals ma, where f is 0. Okay. And now the other thing is, if your Lagrangian is nice, you get that this will be a linear differential equation, and then you'll have uniqueness of solutions.
Oh, up to initial conditions, which we
Yes,
have.
like
Okay.
if see, so from this you see this is a differential equation, right? Because you have some function of qt q dot t, of q
Yeah.
of t, and you take some derivatives, and then subtract some other function of q, and you get 0. So this is some system of differential equations which you want to solve, and if the Lagrangian is a nice enough function, then this is a nice enough system, and you will have uniqueness of solutions and existence.
Okay.
Now, are you actually able to solve this? Sometimes yes, sometimes no. But in Physics 354, I've never solved a single ODE. So usually you just study the behavior of these solutions, or like you solve it. There's like very particular techniques to solve things, which we'll talk about later.
You just said you solved them with ODEs. What?
Hmm?
You just said you solved them with ODEs. How do you know that?
Well, no, you can't solve every ODE analytically.
Okay.
Like you can't. Okay, on a computer you can solve all of this. Well, usually well enough in finite time and with finite computer size, and that's fine. But okay, for everything that we're concerned with, this is fine. Okay.
If you have a system, how do you get Lagrangian?
Great question. And
Hell?
well, essentially, well, meaning experiment. Like at the end of the day, you have to do an experiment to figure out how your system works and write down the Lagrangian for it. Right? And so, for example, so what I told you the Lagrangian for a free particle. I didn't explain why this has to be the Lagrangian for a free particle. In fact, this has to be the Lagrangian for a free particle, at least in R3. And you can prove it directly, and Landau does. It's a little hand-wavy, but it's pretty solid. But then, what you're missing any interaction with other particles. And then you find out that the interaction with other particles is in fact the potential. And we will see that in a little bit. Actually,
This is kinetic.
Actually, we can see it. Well, it's 8:13. I don't want to. Or you can see right now exactly how it's. You can see it right now. It's going to be 2 lines
2 lines in how many minutes?
in 5 minutes. Okay. Suppose I wrote something down and I didn't explain it at all. How's that sound? And you
Right.
either you understand it or you don't. Does that sound like a fair deal?
Sure. It is what it is. I like that.
Okay. So I'm going to so the Lagrangian. I'm going to write down a Lagrangian for for a single particle. No. So suppose my Lagrangian was 1/2 mx dot squared. So kinetic term as always, minus some v of x. All right? Yes, minus some v of x. Now I do the usual thing. What's the derivative of the Lagrangian with respect to x dot? Mx dot. What's the derivative of the Lagrangian with respect to x? Pardon? Yeah, minus the derivative of v with respect to x. Okay. Now I evaluate this all at x of t. So x dot is no longer a symbol. It's now becomes the derivative of x of t. Why? Because I plug in the derivative of x of x into the this slot of the Lagrangian, right? So okay, and now if I do ddt so I just write down the Euler-Lagrange equation, and I plug this into it, minus partial x, L partial x. So this equals 0. Now if I plug this into this, I get what? I get mx double dot minus partial x of v, right? Evaluated, at x of t. Do you agree? Equals 0. But this is what? This is mx double dot is equal to minus partial x v at x of t. Okay, but do people remember what this is from last time?
What is v?
Some function, but do people remember we had v's last time and they were the potential, and so minus derivative of the respect to x of the potential was what was the important? No, what was the most important equation of Newtonian mechanics?
Potentially for
There's one equation in Newtonian mechanics that really matters. It is 3 letters. You have ma, and so you're missing. You have ma, so you're missing f.
yes. Sure.
Okay. So, if you knew what the forces were, last time we figured out how to figure out what the potential better be, right? Do you agree? But now we just showed that actually, if you knew what the forces were and you knew what the potential was, then the Lagrangian that gives you the right f equals ma equation has to be 1/2 mx squared minus v of x, where v is the potential that gives you this force. Okay. So now, if you know Newtonian mechanics, you can figure out what the potentials should be what the Lagrangians should be for most systems. But even then, this potential, you need to know the force. The force is acting on the system, right? In Newtonian mechanics. But if I told you a system, how do you know the forces acting on the system in Newtonian mechanics? Well, the only way to do that is do an experiment and measure the forces and figure out what they are. Okay. Okay, I'm going to stop recording.